Okay, so let's work on solving quiz 7. So there were some irregularities in the writing of this exam or quiz. I'm really sorry about that. I'll point them out here, and certainly that'll be taken into account while grading. One of the big problems here is I didn't put boxes for everything. So for example, this first problem, in which we're looking at this phase diagram, we say that at 800 degrees C, determine the composition range which will yield a microstructure of aluminum nickel, Al(Ni), with aluminum nickel 3 precipitates mixed within. So this is aluminum nickel, this is aluminum nickel 3, which makes this region our two-phase aluminum nickel 3, and you know that because you know that between single phases we necessarily have a two-phase region, and that region extends from here to here. So both the temperature ranges that we're talking about, the 800 and the 1300, are bracketed by that. Above that we have kind of a eutectic kind of like structure, and I'll show you that in a little bit. Below that we have another single-phase region and another set of two-phase regions. So what's essentially happening here is we're having coherent nucleation or transformation of this two-phase region, and if it comes down right at this composition, it transforms into aluminum 3 nickel 5. So that's something that's kind of neat about this phase diagram, is that you have these ordered phases that only exist at low temperatures, and they pop into existence. And naturally then, if you were to cool down and say here, you would get a aluminum nickel, aluminum 3 nickel 5 mixed, and if you cool down into this region, you would get an aluminum 3 nickel 5, aluminum nickel 3 mixed microstructure. But we're only going to work here. So great, we're looking at 800 degrees, and what I was asking about is what compositional ranges you would get a precipitate in a solid parent. So if you remember, in class we had kind of our idealized phase diagram like this, in which we had an alpha, alpha plus beta, beta, beta plus liquid, liquid, alpha plus liquid. And cooling down from there, we'd come down, we'd form alpha plus liquid, and then we come to this point, all the residual liquid would transform into eutectic. So in that region, we would have something that looks like alpha, 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 and then eutectic. I'm drawing this kind of a scratchy lamellar type structure. If, however, we cool down from that composition and that temperature, we would get alpha plus liquid. Here, all the liquid transforms into alpha, and then here, some of the alpha has to transform into beta. So we have alpha, 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 and precipitates of beta, which means that going up here, I'm going to zoom in, that's our two-phase region. That sliver is aluminum nickel plus liquid. That's liquid. And this sliver is going to be actually a little sliver right in there, which you can barely see, is aluminum nickel 3 plus liquid. And if we cool down in this compositional window, we cool down, we make aluminum nickel 3 plus liquid, And then when we reach this region, we form a eutectic with the residual liquid forms a eutectic. If, however, we cool down from here, we form aluminum nickel plus liquid. We form all aluminum nickel, and now we get precipitates of aluminum nickel 3. So we want to be somewhere in this range, and we have to be not here. So that means that our solution is that range, and you can circle it, or I didn't write it down, but you could also mark the range is 0.62 to 0.70. That range goes there. So the next question is at a different temperature, and I chose that other temperature to avoid kind of this hump. At 1,300, which is right there, what compositional range yields aluminum nickel with eutectic microstructure? So there's aluminum nickel, and then it forms a eutectic. So basically, we want this region here. And this then is looking at our very kind of idealized phase diagram, that's that region, right? So it extends from there to our the tip of the alpha where it hits the eutectic temperature to the eutectic composition, and the eutectic composition is there, which is around what? 0.74, and that line is kind of the separating line. If our original was there, corresponds to that, and that left side is the same point in the eutectic. So our range is going to be 0.7 to 0.74. The next question is about the phase composition of the eutectic and the elemental composition. I actually meant phase fraction, but even then, phase fraction is not something that you can get from this. And the reason for that is that we know that we form some alpha, and in fact, you probably could work it out, but it really is not a trivial business. So that is really not fair, and it's the elemental composition that you can solve, and that elemental composition, again from here, that's 0.74. Call this X N I E U T. So the nickel phase fraction that forms the eutectic is 0.74 or 74% nickel. Okay. Next question. In this next question, I ask again 2 parts, but I only gave you 1 box. So if you wanted to, you could kind of divide that box and have the first part and the second part of the question. The first part is asking us about thermodynamic equilibrium, which means that we can basically read from the phase diagram using the lever rule, and we're at T3, which means that we're going to read the the lever rule for liquid, FL is going to be equal to this distance here, this distance divided by the total. So that's going to be 30 minus 19 divided by about 57 minus 19, which is equal to 0.29. And then the phase fraction of alpha is equal to 1 minus phase fraction of liquid, which is equal to 0.71, which, actually it looks pretty reasonable. About 30 to 70%. The next is about composition, which we again read by dropping verticals from where our tie lines cross the liquidus and solidus, and we get XB alpha is equal to 19% B, and XB liquid is equal to 57% B. Next question has to do with how we would read this in non-equilibrium. And in this non-equilibrium, I gave you that the solidus shifts to here. And with that solidus shift, basically it means that now we do exactly the same thing, but instead of the original solidus, we use the new solidus, which is stretched, which gives us a alpha composition of around 15. So F liquid is equal to that distance, which is 30 minus 15, divided by the total, which is 57 minus 15, which is equal to 0.36, and the phase fraction of the liquid is equal to 1 minus the phase fraction of the alpha, which is equal to 0.64. And then, again, the composition is just from dropping the verticals. So XB alpha is equal to 15%. XB liquid is equal to 57%. That's it.